road because so you guys have your lab on Thursday. This Thursday, you guys are going to do a chemical reaction lab. We have 2 chemistry labs. One is chemical reactions and one is PHS, which they're both kind of fun, I think. But we need to talk about chemical reactions, and it's a few parts away, so we'll see how far we get. But up here we've been talking about, you guys know compounds are atoms joined together with chemical bonds, right? We use a formula like NaCl. It's got 1 sodium, 1 chlorine. Now, we talked about NaCl, though, as an example of an ionic compound, because sodium, the metal, will give up an electron and become a positively charged cation, and chlorine will take in an electron and -1. Anyway, so the other type of compound is what we're going to talk about today. That was an ionic compound. We're going to talk about molecular compounds. And we're building up to this thing called Lewis structures today. And what I want you guys to do in this class is just to be able to look at kind of a structure of a molecule and be able to what I call interpret it. And I'll show you what that means. So molecular compounds, we've been talking about them, are going to only have covalent bonds. And covalent bonds are where electrons are shared. It makes for a great t-shirt, like a t-shirt with covalent bonds and 2 atoms sharing electrons. And anyway. Versus ionic bonds, no ionic bonds, no electrons transferred, electrons are entirely shared. Okay, molecular compounds, we said that look for the metal, like on a test, if I ask you if it's a molecular or an ionic compound, if there's no metal, you're going to be like, oh, it's a molecular compound, okay? If there's a metal, like sodium chloride, sodium's a metal, then it's an ionic compound. So molecular compounds, no metals, and we're going to talk about something called Lewis structures. And you've probably seen Lewis structures before, you just didn't know what they were. It's representing what a molecule looks like, how it's arranged and everything. So I have, what is his name? Anyway, I have a video. Good job. So the things I want you to know in this class, you know where he came up with that list of, let's see, how do I say it? I call it a pot of valence electrons. And when he drew Lewis structures, he basically did like a little math, a little addition kind of on the side there. So first off, do you guys remember, it's like if you have your periodic tables, I don't think that happened, I think I gave mine away. But if you look at your periodic table, how do we know how many valence electrons, for instance, sodium has? The group number, perfect. So sodium's in 1A, so it has 1 valence electron. Perfect. So you're going to know how many valence electrons does oxygen have? 6. It is 6. Perfect. Yep, you got it. So we're going to come up with a lot of valence electrons. And then we need to stick these atoms together, and on these Lewis structures, you're going to see a line for a single bond, that's 2 electrons. How many electrons for a double bond? There's 2, how about 2 lines? Yep, 4. There's 2 lines, there's 4 electrons. What about with a triple bond? Yep, 6 electrons. Perfect. You got it. And did you see, and I'll just go ahead and go right to it. When he drew the structure for oxygen, he had these 2 hydrogens, and he had these, I call them dots. They're a pair of lone pair electrons. And those actually are important, and I don't know if I convince you of it in this class, but this would be an example of a water molecule where this black atom is oxygen, hydrogen, and hydrogen. And these actually are 2 electrons and 2 electrons. They actually give a water molecule its shape. And there's other properties about water that are very important that has to do with basically shape. So there's a water molecule. So we definitely, even though the lone pair electrons are like, what do they do? Well, you just have to trust me that in chemistry it matters if they're lone pair electrons or not. The other thing is, I mentioned the pot of electrons, and one of the things I want you to be able to do is look at a Lewis structure like this of water and go, oh, is that the right number of electrons? And so, like, it's a little math, it's that addition thing. One marker is green. Excuse me. with regard to hydrogen, there are 2 hydrogens, and how many valence electrons associated with each hydrogen? 1. And there's 1 oxygen atom, how many valence electrons? For oxygen. 6. It's 6A, yep. Okay, so my total, my pot, is 8 electrons. And so if this is a final Lewis structure, each dash, each single bond is 2. So I have 2, 4, 6, 8. Okay, that's the sort of check I'm talking about. It has 8 electrons. Okay, so that's the sort of check we'll be kind of asking us to do coming up. I'm trying to think, I know it's going to be a little ways till your next unit exam, but I think I'll probably put some Lewis structures that are incorrect. You might be like, one of the things that can be incorrect about them is on the final Lewis structure, the electrons that are there in single and double and triple bonds and lone pair electrons, those electrons don't add up to, this is my pot. So these are Lewis dot structures of elements. So find carbon. How many valence electrons around carbon? 4. Yep, there are 4. And so do you see where this just simply is showing carbon, and each dot represents one of its valence electrons. What is the name of the 7A elements? The fancy name for the group. Halogens, yep. So how many valence electrons for the halogens? 7, yep, so 7A. So we have 2, 4, 6, 7. This actually kind of shows, we'll pick on fluorine, we'll pick on the halogens. You see where, if it's going to connect, and we had, our oldest kid is a boy, and goodness, Craig, is he 28? I don't know, I think so. Yep. He'll be 20, he's 27 now. But like, look how little boys play with cars. And it's almost like, this is like a parking lot and a garage where each atom has 4 garages, and each garage can hold 2 cars. Okay? So, full, it gets 1 car. And that's actually kind of, with regard to the halogens, are all going to look like this, have 7 valence electrons around it, and that's how many things can park next to it. And actually, that's how many times what we say it reaches out. That's the valence. That's how many bonds it can form in general. So, oxygen, 2. Okay, so it can actually, what we say, reach out twice. So anyway, carbon, 4. How many times, how about neon? Any parking spots open? Nope. That's the rare gases. I like what Hank said, he called it octet, and he said it's more of a nudge than a rule. Okay, most atoms want to get 8. 2, 4, 6, 8. They want to get 8. And on our Lewis structures, when we go to see, for you guys anyway, we're going to be looking for 8. Except for hydrogen, hydrogen only wants 2. So Lewis structures, when you see them, basically the symbol, like whether it's an H or it's an O, think of the symbol as representing the nucleus of the atom and the non-valence electrons. Okay. So a bond pair is going to be a dash. Okay. If you see 2 dashes, you guys told me that's 4 electrons. That's called a double bond. If you see 3 dashes, I like what he actually talked us through nitrogen. And nitrogen is a diatomic element, so that means diatomic just means there's 2. So as nitrogen's floating around this room, about 80% of the gas we're breathing is nitrogen triple bond nitrogen. How fun is that? Lone pair electrons on our Lewis structures. Okay. Now, Lewis structures can get more complicated than we need to cover. But we're going to go with them always in pairs. Electrons always in pairs, whether it's lone pair electrons or as in a single, double, triple bond. I like what he also said. There's no such thing as a quadruple bond. I'm like, are you sure? I guess so. Sure, you know what I'm talking about. This whole, whether it's north, south, you know, east or west, it does not matter. Okay, and it's interesting. Sometimes I'll walk around students we do their loose structures and they look a little different. That's fine. It really doesn't matter. Now, when we draw Lewis structures, obviously it's going to be planar, flat, on paper like that. But actually, we can think three-dimensional. So, for instance, this water looks like this, but thinking three-dimensionally, it really is like this, spatially. All right. So let's pick on ammonia. So ammonia would look sort of like this. And now I'm kind of switching up. I have a nitrogen atom in the middle. Ammonia is NH3, so I have 3 hydrogens here. Okay, again, this is my lone pair electron. If you look at it like this, you can kind of see how the nitrogen has a complete effect. So what I'd like to do here is to kind of, in your notes, get down, and if you have this on a test, I'm looking for this little mathematical operation, kind of like I did with water, to get 8 valence electrons. So, nitrogen. There's 1 nitrogen atom. How many valence electrons? From its group number? 5. Yep, 5 valence electrons. With regard to hydrogen, there are 3 hydrogen atoms. How many valence electrons? 1, just 1. So we got 5 up there. We got 3 here. So that's 8 valence electrons. So again, I like what Hank said. Sometimes I show you movies I hadn't Shedson before I watched, but I like what he said. If this pot, I call it pot, doesn't match on your Lewis structure, then something's wrong. So is this what's shown on the Lewis structure? 8? I think so. 2, 4, 6, 8. Yep. So that is indeed correct. Does each atom have a complete octet? What wants a duet? What do I mean by duet? 2, yep. So what wants 2? Hydrogen just wants 2. What rare gas, rare gas, inert gas, group 8A element, what rare gas has 2 electrons if it's neutral? Helium, yep, that's helium. Yep. And then just kind of a follow-up question. How many pairs of lone pair electrons are there in the structure? How many pairs on the sun's factors? 1. There's just 1 pair, exactly. Only 1 pair. So if you see a question like that on the test, that's kind of how you get into that. Okay, we've got a few more. Formaldehyde. So let's go ahead. The formula is H2CO. So let's kind of go from left to right. Hydrogens. I've got 2 of them. How many electrons, valence electrons, do hydrogens have? Just 1. Yep. So collectively 2. Carbon. There's 1 carbon atom. How many valence electrons for carbon? 4. Yep. Collectively 4 electrons. Oxygen. 1 oxygen atom. 6. 6 valence electrons. 6. You know, I kind of tease, feel free to grab a calculator. But I'm looking at 12. And then let's go over here. So how many valence electrons are there in this double bond? There are 4. So if I have 4, 6, 8, 10, 12. So that's what I mean by it does match. Now, this question about, I like what Hank said about, I call it kind of joint custody sometimes. Go ahead and clear this. So you told me there's 4 electrons here in this double bond. So this carbon shares 4 electrons with this oxygen. So we end up kind of with, I think of them almost kind of as Venn diagrams with overlap. So that carbon atom has 2, 4, 6, 8. It has a complete set of 8 electrons. I'm going to make another Venn diagram around my oxygen. Again, with this joint custody with 4 electrons here, we have 4, 6, 8. It's got 8. And then, of course, the hydrogens are the duets. Okay, so the answer there is yes. Okay. The last one. How many pairs of lone pair electrons are there? 2. Yep, very good. All right, pot of valence electrons, 2 hydrogens. You guys told me 1 valence electron for each of them, collectively 2 electrons. Carbon, there's 2 carbon atoms. You guys told me 4 valence electrons there, so we're looking at 8 valence electrons for them, 10 electrons collectively. Let's see, how many electrons are there in that triple bond? Yep, there are 6. So I got 6, 8, 10. So I do have 10 electrons on my final Lewis structure. And they each have a complete octet. So if there are 6 electrons here, I can draw a circle around this carbon. I got 6 plus 2 is 8. I can draw a circle around this carbon. I have 6 plus 2 is 8. And hydrogens are duets. So that's awesome. How many pairs of lone pair electrons? 0. 0. Okay. Boy, hey, let's see what we got here. Let's start with our carbons. Let's count how many carbons we have. 5 carbons. You guys told me 4 valence electrons. So we have 20 electrons. Hydrogen, I'm looking at maybe 1, 2, 3, 4, 5 hydrogens. You guys told me 1 valence electron, 5 electrons. Oxygen, there's just 1 oxygen atom. It's 6A, so it's 6 valence electrons. 1 nitrogen. How many valence electrons for nitrogen? 5. Yep. 5A, 5 electrons. For the Lewis structures we'll be drawing, hopefully we should get an even number, which it looks like we do. So let's see, that's 36. Yowza. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Well, I get 36. Score! I'll say the answer to this next question is yes, because all these Lewis structures were drawn correctly. But again, on your test, that may not be the case. You were to go ahead and find any atom other than hydrogen, draw a circle around it, you would see that it either has full possession or joint possession of 8 electrons. Oxygen, 8 electrons. This carbon, 8 electrons. That carbon, 8 electrons. This nitrogen, 8 electrons. So how many pairs of lone pair electrons are there? Oh, fingers. How many pairs of lone pair electrons are there? 3? Yep. 3. Oops. 3. There are 3. Perfect. So I brought these structures in, and I'll put these on the board, I think. They're just hydrocarbons. A hydrocarbon contains hydrogen and carbon, go figure. So the first one is C2H6. And the next one is C2H4. The next one is C2H2. And they look like this. For the first one, they all have carbon and carbon, carbon and carbon. For the first one, we have 3 hydrogens on both carbons. And it looks like this, where you can see the carbon atoms and you can see the hydrogen atoms. Now, the gray thing are where electrons are shared. So that's the chemical bond. This is C2H6. The other one, or the next one, actually the carbon has a double bond. The 2 carbon atoms are double bonded, and then they each have 2 hydrogens. Now, if you go into chemistry, we'll talk more about when you have a double bond. The first bond to get there is normal. So actually, it's going to be this gray. So this is C2H4. So you can see the gray between the hydrogens. That's normal. Single bond. And then between the carbons, we actually have a gray thing there. So that's what we call the first to arrive. It's got a different characteristic. It's what we call the signal bond, primary bond. And then this purple and pink, that is actually the secondary bond that makes it a double bond. So it's kind of cool that actually when we have to go ahead and make it, instead of a single, a double bond, that extra bond is different than the first bond there. That's what we call a secondary bond. So the secondary bond actually kind of what we say lags outside of the single bond. So to make that second bond, it's a purple and pink. So we end up with a shape kind of like, if you ignore the purple and pink, it's actually what we say planar. If you compare that to this is not planar. This is C2H6. This is planar. Well, you probably know what's going to happen. The last one, actually you're going to see a gray, then you're going to see 2 pink and purples. So this is a triple bond for this structure. And then it has a hydrogen on either side. This is what I call the hot dog shape. So this is the C2H2. So again, you can kind of see the gray there. And of course, we have a gray connecting the hydrogens, just like we did before. But now actually, to get the triple bond, after the primary bond, we have 2 secondary bonds, secondary. So this is triple bond. And again, if we blow off the 4 electrons making after the first 2 go arrive, it makes what we call a linear shape. So C2H2 is linear, and C2H4 is planar. This guy right here, I'll steal that. Have you heard of benzene? Okay. This is actually benzene, where if you look closely, you'll see all it is it's got 6, again, carbons, and each of the carbons has a hydrogen. So this is C6H6. And then this purple and pink, that's just the extra electrons making that double bonds. So benzene looks like this. I used to be better at drawing benzene rings. Okay, so it has 6 carbons. So 1, 2, 3, 4, 5, 6. Goodness gracious. Well, that's the primary bonds. And then let's go ahead and make the little hydrogens. I've mentioned this about Christmas time to my other chemistry students that I think this should be Christmas ornaments because it's ring and benzene ring. But now the way benzene, excuse me, does is it alternates. So it has a single bond here, and now it has the secondary bond, or the double bond. Single bond here, double bond here, single bond here, double bond here. So what we says alternates. And actually, not to totally confuse you, but it goes back and forth. If I were to redraw my 6 carbons, goodness, my organic professor would be so frustrated. So I'm going to alternate them to the different carbons now. Single, double, single, double, single, double. And these are hydrogens. It actually goes back and forth between these two. In my defense, usually instead of doing all this, we kind of draw as, you might have seen these in literature before, or that's the same thing. This is benzene. So we usually don't draw all those carbons and hydrogens. We just draw this excited thing with a circle in the middle to kind of show the cool thing about benzene. Well, yeah, just a few minutes, like we are going to take a look at the next one, okay? Okay. So it's like, oh my gosh, I've seen this before, and you have. This just is so right. This just focuses on, I'll give you, let's pass this down. This just focuses on mixtures. So can someone give me an example? Oh, thank you. An example of a homogeneous mixture? What do you think? You could kind of tease and like if somebody got like my husband had jaw surgery done years ago. So he has jaw surgery, then you have to like make everything homogeneous to feed them to a straw. So you could make pizza homogeneous mixture simply by blending it up well enough. A homogeneous mixture is just well blended. Okay, and a heterogeneous mixture is chunky. So you could actually look at peanut butter. Chunky peanut butter would be a heterogeneous mixture, and smooth creamy peanut butter would be a homogeneous mixture. So the word that I hid, see I hid some words, it was so fun, was physically combined. So what you do is go ahead and toss, just throw 2 or more pure substances together. So what goes in that next blank? A blank mixture has the same composition throughout. I'm going to go around the room. I'm going to put everybody on the spot. You guys didn't do anything wrong, but okay, Kate. What goes in the first blank?
Homogeneous.
Homogeneous. Very good. Okay, Hannah. What goes in the next blank? It would be heterogeneous. Perfect. You guys got this. One of the things I don't want to do is make it more complicated than it is. Okay. So I think it just should hopefully go left and right. Just looking at the pictures, what do you think, Mackenzie? What do you think the left one? Would you call this homo or heterogeneous? I would call it homogeneous too. Very good. Nadira, what would you call the next one? Heterogeneous. Perfect. Very good. You got it. You got it. I'm not going to put you on the spot, Jasmine. Each substance retains its own chemical identity. I'll put you on the spot for this one. I bet you know it starts with actually the letter V, Jasmine. So the point is, like, if you're making Kool-Aid, I was kind of teased that our daughter used to make it with like 2 cups of sugar. I don't know if I do it, but I make it like this. Is it just supposed to be 1? No. It's supposed to be make Kool-Aid. But my point is that if you're making a sugar solution like Kool-Aid basically is, you can have different amounts of sugar dissolved in water. So the word is just letter V. You can, the ratio of its components can, you're like me something. I'm not a good word person. can be different. So what's another word for different? It can vary. My bills are kind of messed up. They can vary. Thanks for playing along with Jasmine. Let's see. Let's see. I'll just say, because these are hard. But the cool thing about mixtures is that you can actually get your individual components back. So a mixture can be separated back out by physical means. Okay, Jasmine, here's one for you. So I like this picture. Kind of, we talked about nitrogen, and here's nitrogen, and this is N2 and oxygen. This would be like what we're doing. Do you think this is a homogeneous mixture or a heterogeneous mixture? The air that you're doing. Why do you think it's heterogeneous? It doesn't look even. It does not look even. It looks chunky there. But actually, it doesn't look, but it is. It's like well mixed. And I think one of the things is like if you're walking around, just walking around, you don't have to worry about running out of oxygen here or there. Oxygen is kind of the same thing. I know. Very good. Ian, what about down here? This is supposed to be ocean water. And what do you think? Homogeneous or heterogeneous? It does look pretty homogeneous, but it's hard to tell with the picture. I'm going with homogeneous. Yeah, very good. Let's say those are both kind of homogeneous. Although I can see that this looks like heterogeneous. They are both homogeneous. Okay, so in physical science, if somebody says, oh, I've got a solution of X or a solution of Y, blah, 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 usually they're talking about a homogeneous mixture. There's far too many S's, and I'm not going to put anybody on spot for this one. Solutions are usually homogeneous, okay? And we talk about the solute that is there in lesser amounts, and the solvent that is there in greater amounts. So oftentimes, you know, to me, if you have a problem with it, I usually make my solutions up in a beaker, and I have a solute. I'm kind of a picture person sometimes. That's a little bit that's added to the solvent. And then, visually speaking, if we take the solute plus the solvent equals the solution. Again, too many S's. Like, please. So that's kind of what that looks like. My bolts are weird again. So the word is aqueous there. An aqueous solution means that water is the solvent. And you'll see it abbreviated as AQ. It's aqueous. I think this last little topic will hold. I think we're bumping up against the time. So we'll finish this on Wednesday and then start chemical reactions, and we should be in good shape for Thursday. That's the plan, yeah.